In this example, we look at a drug that is administered to a patient at the same time every day. Supposing that the concentration of the drug is Cn, measured in milligrams per milliliter, after the injection on the nth day. Before the injection the next day, only 30% of the drug remains in the bloodstream, and the daily dose raises the concentration by 0.2 milligrams per milliliter. Find the concentration after 3 days. Well, let's assume that at C0, they're starting with 0 milligrams in their bloodstream. So after the first day, there's 0 milligrams, so 30% of that remains is still 0. But then we're going to add 0.2 milligrams to that. After the second day, then the amount that was that we started with the previous day has reduced to 30% of that. And then we're adding another dose of 0.2. And then by the third day, well, we're taking the amount that we had C2 here, and that's going to be reduced by 30%, and then we're adding another 0.2 to that. So notice what I did here was I take the previous day's concentration, and here it was multiplied by 0.30 because it reduces by 30%, and then we add another dose of 0.2. So here then I would take this amount here, and it would get put into this part here. Right, so we're taking the amount from the previous day, multiplying by 0.30, take 30% of it that remains, and then adding a new dose of 0.2. And just to kind of verify that what we're doing here is really something we can generalize with a formula, let me write it this way. So it's 0.2 plus 0.3 times 0.2, and then here we'd have 0.3 times 0.3, so 0.3 squared times 0.2. If I were to do another day, it would be adding in another term, 0.3 cubed times 0.2. And yeah, so this is just following sort of a generic pattern. To get the concentration on the next day, we take the previous day's concentration, multiply it by 0.30, and add 0.2. So this formula here would give us the concentration after 3 days. Okay, you can sum those up to get the value. What about after the nth dose? So if we were to continue this pattern, we would see that it is in fact a geometric series. Right, so continuing that pattern, I see it's a geometric series with the first term is 0.2, and the common ratio is 0.3, so I'm multiplying 0.3 to go from one term to the next. So we know since it's a geometric series, we can use the partial sum formula for a geometric series. So it's A1, which is 0.2, 1 minus 0.3 to the power of n, over 1 minus 0.3. So that's using my geometric series partial sum formula. this could also be simplified a little bit. 1 minus 0.3 would be 0.7, and then 0.2 divided by 0.7 would be 2 over 7. What is the limiting concentration? In other words, what happens as I take n to infinity? And we notice here, we can use the Cn formula that we had in the previous slide. So this would be the limit as n goes to infinity. 2 over 7 times 1 minus 0.3 to the n. And as n goes to infinity, 0.3 to the n will go to 0. And so this will just be equal to 2 over 7 times 1 minus 0, so 2 over 7. So after many days of applying the drug, you'll have a consistent amount of concentration of 2 over 7 in the bloodstream. In this example, we want to write the repeating decimal 2.317 bar, so in other words, it's repeating the 1/7 part, as a ratio of integers. Now with any repeating decimal, you can always write it as a geometric series. Like for instance here, if I take 2.317 repeating, I can take the 2.3 part aside, that's not the repeating part. And then the repeating part would be 0.17, or 0.017, and then another 0.00017, and then another 0.0000017, and so on. So you see this 1/7 part that's repeating will be the part that we can express as a geometric series. So in this case, it's starting with 0.017, and then I'm multiplying that by 0.01 to generate the next term of the sequence. All right, you can see that here the common ratio, when I multiply 0.017 times 0.01, it's going to scooch the decimal over 2 spots to the left, so that would give me this one. And then I multiply that by 0.01 again. It scooches the decimal 2 more spots to the left. So there we have a way of expressing it as a geometric series. So since it's a convergent geometric series here, the common ratio r is equal to 0.01. It's certainly less than 1 in absolute value. So, and then the first term would be 0.017. Right, here we can express the sum of the geometric series as a fraction. Now to express it as a ratio of integers, we just have to do a little bit of arithmetic to simplify this. Right, so this would be 0.017 over 0.99. Then I can move the decimals over, so this would be 17 over 990. And then I can combine these guys. So 2.3 can be written as 23 over 10. And then getting a common denominator, I'll multiply 23 over 10 by 99 over 99. So 23 times 99 is 2277 over 990 plus 17 over 990. And combining those, we get 2294 over 990. And just to double check here on my calculator, I'll do the division of 2294 divided by 990 and see that we get the repeating decimal that we started with, 2.317171717. In this example, we want to find the sum of the series x to the n where the absolute value of x is less than 1. Well, notice that this is just a geometric series starting with n equals 0, so starting with x to the power of 0, which is 1. We're just multiplying each consecutive term by x. So the next one would be x 1 plus x squared plus x cubed, and so on. So it's geometric, and it's got the first term is 1 and the common ratio is x. Since we were given that the absolute value of x is less than 1, we know it's convergent, and it converges to a over 1 minus r. In this case is 1 over 1 minus x. And this series will be convenient for us to take note of now. This one will become handy later on when we want to express functions of this form, 1 over 1 minus x, as an infinite series.